Up to this point in our discussion of bending beams, we have focused strictly on the pure bending case. That is, locations along a beam where the shear force is a zero. Now what we're going to do is come back and look at the more general case where both a non-zero shear force and non-zero bending moment exist. What we know from the bending moment results from before still hold true. The bending moment gives rise to a normal component of stress, which is minus my over I. Said in a different way, if you take the resultant of that sigma x over the cross section, you get the resultant there of m. The shear force we know is the resultant of the shear stress. The shear force we can find from equilibrium. The shear stress we need to use a theory to understand what that's going to be. In the end, of course, is that the resultant of that shear stress must be equal to that shear force of V. Suppose we look at a cross-section of the beam. I just arbitrarily chose a trapezoidal shape beam just for the sake of discussion. And what we're interested in is at some position Y to be able to predict what the shear stress tau is going to be on that face. Let's look at the final result from this. We'll find out that the shear stress tau is going to be equal to the product of the shear force V with this parameter here of Q, which has to do with the centroidal properties of the area above Y. So again, if this is Y, we're looking at the area above there. A star is the area of that. Y bar star is the centroid of that. Multiply those two together, that gives you Q, and then we divide by the second area moment I, and also divide by the total net thickness there of T. That is going to be a result. That is how we're going to use it. But let's see from where that comes. In order to see from where that comes, let's think about what we've seen from before. If we look at a stress element at a cut in this beam, that stress element needs to reflect two things. It needs to reflect that normal stress, which is coming from the bending moment M. So since this is above the neutral plane, we see that with the moment that's given here, the upper part's going to be in compression, and hence that's the way we drew the sigma. The shear stress is going to be pointing the same direction as the shear force, because that shear stress comes from that. But an important result is that when we have this transverse shear stress of tau xy, we know that the shear stress must appear in groups of 4. Okay, this stress and this stress, these two components of stress are the same, but opposite. These two here are equal and opposite, and they're oriented in such a way that they put a moment which counteracts the moment of the other two. Therefore, the conclusion is if tau xy here is down, then tau yx on the bottom must be to the right. The point of this is that this transverse shear force V actually gives rise to a longitudinal shear stress component, and that's the basis on which we're going to derive our relationship. We're looking here at a beam with some arbitrary loading on it. I take a section of that beam, a section of width of x, of delta x, that's this dimension here. And as I cut this away, I'm going to have a bending moment on the left, bending moment on the right, which will likely be different. They have a shear force left, shear force right. I'm going to focus in on what the bending moment M does. We know that since the stress is going to be my over I, above the neutral axis, with M shown as it is, it's going to be sigma in compression, and on the bottom it's sigma in tension. And these are the two equations we have for the normal stress on the left and the right side. Now, and when we look at a cut through that cross section, we're going to slice off the very top part of this. So we find the resultant force on there due to the normal components of stress. That is, I integrate the stress over the area, and that area I'm calling it A star, because that says that the area above wherever we have defined our y. And then the resultant force on the right side is this. So as we talked about in the explanation video on shear stress, we know that since we have a shear force transversely, we're going to have a longitudinal shear stress. And this delta H, that is the resultant of that shear stress. Okay. Well, two things we need to do. First thing we need to do is relate delta H back to the F's. So as I take that FBD above, if I sum forces in X, F of X on the left side, F of X plus delta X on the right pointing to the left plus delta H, we see that this resultant shear force is the difference between the resultant forces due to the normal. So here we begin to see our connection between the bending moment M and the shear stress that develops in that beam. Then we go back to our definition of what a shear stress is. We take the resultant force, that's that resultant force of delta H there on the bottom up here. If I divide by the area over which it acts, it's delta X in X. T is the dimension back there in Z. So this is basically force divided by the area over which it acts. We let delta X go to a 0. We use our result there from above, and we get that tau is equal to 1 over T dF dx. It's an important equation, but not one yet that we're ready to use. So if we go back up to our result above, we see that the resultant force is the is the integral of the normal stress over the cross-sectional area. This my over I, you might recall, is equal to the sigma. And importantly, this is probably a very critical step here. If what I have left here is the integral of y over the area, this, by definition, is equal to that. By definition, if you take the values of y over in the area, integrate them, you end up with that area times the centroid there of y bar star. We pull everything together. We put that back into our expression for df dx, and we get this. And finally, we end up with this result after we use an equilibrium result from above that said that the shear force is equal to d in dx. This is a very important critical equation. It's going to be what we're going to use in general for the development of a shear stress on a cross-section passing through sort of the line of symmetry there of the cross-section. So that's going to be our go-to equation. Let's actually put this to use and come back later on in the next lecture and talk about the consequences of this. But what I would like to do is apply that to a very common cross-section, and that's the rectangular one. If I want to write down an expression for the shear stress on a cross-section of a rectangular cross-section beam, what I need to do is that for a given value of y, I need to look at the area above that. And the two things I need from that is to actually find the area of that piece. That's what we call A star. And so for some given value of y, we see the area then is given by this dimension right here, which is equal to h over 2 minus y. It's got a thickness there of t, so that's A star. Then the centroid of that, which is y bar star, that's going to be equal to the average value of h over 2 and y. That it's going to be halfway between here and there. Okay? So I take the average value, h over 2 plus y divided by 2, and I get this. I substitute these two into our expression of tau is equal to v a star y bar star divided by it. I substitute those in, and I get this. I multiply it through, and this is my expression for tau. What this says is that if I look at a cross-section of this rectangular cross-section beam, I draw in my neutral plane, it says that the shear stress is going to be quadratic in y. This is y, and this red thing here is the distribution there for tau. With tau being, I think we said in our derivation, tau is a result here of our resultant shear force there of V is down, so tau is going to be down. And a second important result from this is that the maximum value occurs at the neutral axis where y is equal to 0. So this here is tau max. Well, what is the maximum? Well, that's going to be when y is equal to 0, and we can see here that that ends up being 3/2 v over a. An important thing to observe from here is that earlier, when we talked about shear stress in bolts and pins, what we said was that the shear stress was pretty close to being the average. We just found the average by taking the shear force and dividing it by A. Turns out, we can see here that when bending is involved, that's not a very good representation. We're actually off by 50%. This is 1.5 times that. That's probably worth writing it down. 3 halves times the average value of the stress. So if you just use the average as the maximum, you'd be off. Okay, so I would say then that what we need to think about here is that, let's go down to this page right here. In general, when we have a bending moment M and a shear force V at a cross-section, what we know is that the moment gives rise to a normal stress, which with the M as shown, it's going to be in compression at the top, tension at the bottom. It's going to have a maximum normal stress at the top and at the bottom. The shear force here of V is going to produce a shear stress. And for a rectangular cross-section beam, this is our expression here for that. And we see here that the maximum occurs at the neutral axis. It's a 0 at the top and at the bottom. So in conclusion here, if I look at how the stress elements look for these points of A, B, C, D, and E, A and E effectively look the same. We have no shear stress. We have only a normal. The difference between A and E is that at A, it's in compression. On the bottom here, it's in tension. If we now focus in on C, we have just the opposite. We have no normal component of stress, but we have a shear stress, and that's a maximum there. So that's how our element looks there. At B and D, sort of partially between A and C and C and E, it has both a normal component of stress and a shear component of stress. Both of them less than what the maximum is. So here is a case as a result of both a shear force and a bending moment resultant at a cross-section. We have a state of stress which is made up of both normal and shear components. How they're oriented depends where you are on the beam, as well as how large are those components. So in our next class, we're going to be looking more just at using these equations and importantly, trying to understand the distribution of shear stress from our shear stress equation.